So if 10% of people write left-handed, let's see if that breakdown is equal for men and women. So in other words, what we're going to look for is to see if there's some kind of relationship between writing left-handed or writing right-handed and gender. Is there some kind of association? So let's remind ourselves of some more things before we really dive deep into this. What does it mean for two things to be independent? So if I was to write down a definition, A and B are independent if what? And B are independent if what? What do I fill in next? Anyone?
If they don't relate to one another, I don't know the exact words, but I know if they are separate from one another.
All right, if they're separate from one another, let me hone that in this way. If the outcome of one
Doesn't affect the other.
doesn't affect the other. Good. Doesn't affect the probability of the other. And that's what we're really going to test for in this section is, are these two variables independent? Now these are going to be independence in the statistical sense, not in the probability sense. Probability and math are a little bit more rigid than we're going to be in statistics, but that's what we're going to deal with. Now when working with these things, we're going to deal with what are called chi-square, or excuse me, not chi-square, contingency tables. So our contingency table is going to consist of data that represents frequency counts. And we're going to end up with a chi-square test for association from that. Basically, the way we actually calculate our chi-square test, and you don't have to necessarily know this, is going to look like this. Our chi-square test statistic is going to be the sum of the observed minus the expected squared divided by the expected. So maybe I should have written that to look more like a sigma than I did. Let me try that again a little bit. So the sum of all these. Now you might say, well, isn't that the same thing we used in the last section for our goodness of fit test? And I'd say, yeah, except that in this case, the way you calculate your expected values is going to be a little bit different. And fortunately for you guys, you don't have to actually calculate those expected values. That'll be calculated for you. Now in your chi-square tables or your contingency tables, you're going to have a number of rows and a number of columns. The degrees of freedom for this test, so degrees of freedom is going to be R minus 1 times C minus 1. What do you think R and C are going to stand for? So this is going to be number of rows. How do you think, what about the C? Number of rows and number of columns. Now you can do this for pretty much any size table that you want, as long as your expected frequencies are at least 5 in every position. So, okay. Well, let's see here. Let's actually jump in with a chi-square test. And this first one is going to be for whether or not polygraph actually seems to work. Is there an association between those things? The one thing I want to stress here with your chi-square test, and I think I've put this in the handouts that are available online. Just take kind of a quick look here. Handouts, chapter 11. Here we go, chi-square test for association. Your basic null hypothesis is going to be different than what we're used to. at least from chapters 8 and 9. So your null hypothesis is going to be that the row and column variables are independent, and the alternative is that there's an association between those two. Now we got to be careful, Anthony, that we're not going to go beyond the idea of an association. It's just there's some kind of relationship. We're not saying if one causes the other or not. There's just an association. Now when it comes time to writing this on an exam, what I'd like from you is for you to actually fill in row and column with something descriptive of the problem. Don't just tell me row and column. I'll be pretty unhappy with that. But once you describe it, that's fine. Your alternative is that there's going to be an association. So let's start with Elijah.
So I can copy down the formula.
So is this what you're looking for?
Yeah.
Okay, sure. So let's start off with the first part here, which is a chi-square test for association in a polygraph test and the results from that polygraph test. So let's see, do I have that here? I think I do. So let's zoom up here. The table below includes results from a polygraph, which is a lie detector experiments conducted by researchers. In each case, it was known if the subject lied or did not lie. So the table indicates when the polygraph test was correct. Use a 5% significance level to test the claim that whether a subject lies is independent of the polygraph test indication. Do the results suggest that polygraphs are effective in distinguishing between truths and lies? All right. Let's start out with stating HO and HA. And, you know, I'll be pretty relaxed about this as long as you're saying something similar to what I'm going to say right here. So our first step is always to state HO and HA. HO is whether a subject lied and the results from a polygraph test are independent. Okay, cool. How about this next one? Well, here there is an association between the results of a polygraph test and whether the subject lied. Like I said, there's some flexibility in this, but the basic things I want to see are right here. I want to see that these two results are independent in the null hypothesis, and then there's an association in the alternative hypothesis. And then kind of describe what's going on, you know, in terms of the rows and columns. Typically speaking, what's our second step? Raise? All right, significance level. What's our significance level in this one? 5%. Thank you. Step 3 is typically to enter our data. So let's work on that. For that, we're going to need our data, which is here. We're going to enter this into StatDisk. And let's go up to here. I guess I can get rid of this. Clear that. So we're going to enter 18. And then down below that, 34. And then up to the top here, 37 and 15. So not too hard as far as entering the data is concerned. But where do you think I'm going to go to actually run this test? Where do you think, where should I go? Where should I look anyways?
Analysis.
Yeah, analysis and then contingency tables. And as far as it goes, it's not that hard to perform this analysis. So we want to select our columns, which are 1 and 2. Now, if you want to kind of end the suspense a little bit early, we've got 2 rows and 2 columns. Let's see if we can't predict our degrees of freedom. Remember, it's going to be rows minus 1 times columns minus 1. So how many rows are there? 2. How many columns are there?
2.
So what's 2 minus 1 times 2 minus 1? 1 times 1 is 1. So there should be 1 degree of freedom associated with this test. Basically, this is the smallest table for which we can do this kind of analysis. So let's see. Let's click evaluate and bang. What is it that I typically get at this point? Yeah, our p-value. Good. So our p-value is 0.0002. So, Justin, what's that saying about H naught? Yeah. Yeah, we're going to reject H naught. Our p-value is less than alpha, so help me out, finish the sentence. If the p-value is low,
HO must go.
HO must go. All right, good deal. So p is less than alpha, therefore H naught is rejected. Now for step 5, you're kind of, this doesn't exactly fit nicely into our little wording the hypothesis conclusion. So that was this stuff right here, but we don't exactly have parameters and an equals kind of thing here, so we can't fit that in perfectly. So just kind of do the best you can. In this case, I would say the sample data support the claim that, now if the sample data is supporting a claim, it's going to be here in the alternative that there is an association between lying and the results of a polygraph test. And that's it. That's as far as you can go with this conclusion. Can't really say much more beyond it than that. Now it's tempting to say, oh, well, hey, we should use lie detectors then, right? Maybe, I mean, there's an association between these two. Well, let's look at this a little bit more carefully for just a minute. Can anyone tell me where the correct decisions are on this table? Which numbers represent a correct decision as far as the polygraph test is concerned?
37.
37, sure. If the polygraph test indicated that they lie and they actually lied, that's a correct decision. Where's the other correct decision? 34. So 71 times out of just over 100, like 104, you're getting the right answer. I mean, that's good, but it's not ironclad proof that somebody's lying or not lying. It's just not there. And I don't think really lie detectors are used very much in courts because their failure rate is around 30-some%.
Yeah, they don't hold up in court, you can't use it as evidence. in
Yeah.
court, yeah.
Okay, yeah, I'm not surprised, I'm not surprised. All right, in any case, that's our conclusion. There is some kind of a relationship. I mean, yeah, they do better than maybe just guessing, but they're not good enough to use in court. So, thanks, Melanis. Let's move on to example B. And let me get that one up here for us. Let's see, do I put it in here? Yeah. The table below summarizes data from a survey of a sample of women using 1% significance level, assuming that the sample sizes of 800 men and 400 women are predetermined. Test the claim that the proportions of agree/disagree responses are the same for subjects interviewed by men and subjects interviewed by women. Does it appear that the gender of the interviewer affected the responses of women? All right, well, let's have at it. So example B. O. Agree/disagree responses are independent of the gender of the interviewer. So again, you're explaining what each row and column represents, and then we're going to go to it and add in that word that I want to see, independent. For the alternative hypothesis, it's just that there's an association. There is an association between the gender of the interviewer and agree/disagree. All right, so kind of tedious there. Not much we can do about that, but that's your null and alternative hypothesis. So make sure I get those two buzzwords in there, along with the descriptions of the problems. This time we're going with a 1% significance level. And let's input some data. So another kind of quick look at the data here for us. Let me go back to the sheet. We have 538 men who agree with women, 262 men who disagree with women, and then 370 respectively for that second column. Let's put that into StatDisk. So go back to the main page, clear that stuff out. And let's see, it was 538, 262, 330, and 70. Nice, nice. All right, so that's our data. We input the data. Step 4, what are we looking for in step 4? P-value. Good. So let's do our analysis. Go to the analysis submenu, or analysis menu, and then down to the contingency table submenu. We again want columns 1 and 2. Now, all our examples today are going to be for just 2x2s, but you can do any size table that you want. It doesn't have to just be 2x2, but some good and interesting examples presented themselves, so that's why we're going with it here. We'll change this to 0.01. That's not really going to make a difference in terms of your p-value. It's just going to make a difference in terms of the plot and your critical value. This is the point, past this point, that you would reject H naught. So if your test statistic is greater than this, then that means that you would reject. If you actually took the time to go to the chi-square distribution with 1 degree of freedom and find the area to the right of 30.989, then you'd see that that probability is almost 0. In any case, we got our p-value is 0, so p-value is 0.0000. Now for this problem, Jasmine, we decided that alpha was 0.01. Would it have mattered to our decision if we made alpha as 0.05 or 0.01?
No.
No. You'd be rejecting either way. So H naught, or if P is low, H naught must go. So therefore reject H naught. So you can say things a couple ways. You can say the data support the claim that HA is true, or the data reject the claim that this is true. Either one. So I guess for variety, this time I'll say the data reject this possibility. Data reject the claim that agree/disagree responses are independent of gender, or of the gender of the interviewer. So that'd be one way you can say it. I would also accept there's an association, or the data support the claim that there's an association between the gender of the interviewer and agree/disagree. So, or the data support the claim that there is an association between the gender of the interviewer and agree/disagree.
So.
Question on that?
Should we answer it on the list?
You know, I don't think you're gonna be entering this like this into the homework. They'll probably give you some statements and then you just choose the one that you like best. So it's not gonna be like that there. On the test, you're gonna have to choose one of these, but either one is fine.
Okay.
Yeah. So thanks for the question. There's some other chatter, some questions here maybe still, something lingering about this. You know, the important thing here is to understand the limits of what you can conclude with this test. All we're concluding is that there's some kind of relationship, an association between, you know, gender and agree/disagree. We're not saying exactly what it is. And in particular, the one thing we can't say is that one causes the other. That's a separate analysis, it's more in depth, etc. It's something I hope to go over with you at some point. But for right now, as far as we can say is that there's an association. So I was asked a question about this in my morning class, to describe a little bit more about association. And what I want to distinguish here is that association is not causation. It's not as if the gender, we can say, based on this analysis, it may be true, but we can't say that gender causes one response or another, agree or disagree. So for instance, there is an association between the number of sunburns and the amount of ice cream consumed. Now that's an association. It might be a correlation, but is it a causation? Does consuming more ice cream cause more people to get sunburns? Does that make sense? No. So what's going on there is that when do you most like to eat ice cream? What time of year?
During the summer.
During the summer, when it's warm and when you're outside more, maybe you're catching some rays at the beach, whatever. And that's what's causing more people to get sunburns and also causing more people to eat ice cream. So though there's a confounding variable in that relationship of sunburns and ice cream, and it's that confounding variable that's really the cause. All we can say here when we're doing these types of tests is that there's an association, and that's as far as our conclusion can go. So keep that in mind, because that's something that I tend to test when I test you on this kind of material, is are you coming to the right conclusion that we're going to limit ourselves to just a test of an association. Okay, let's keep going. So this next story is actually a real story. Or the next problem is actually a real story. Alert nurses at Veterans Affairs Medical Center in Northampton, Massachusetts noticed an unusually high number of deaths at times when another nurse, Kristen Gilbert, was working. Those same nurses later noticed missing supplies of the drug epinephrine, which is a synthetic adrenaline that stimulates the heart. Kristen Gilbert was arrested and charged with 4 counts of murder and 2 counts of attempted murder. When seeking a grand jury indictment, prosecutors provided a key piece of evidence consisting of the table below. Use a 1% significance level to test the defense claim that deaths on shifts are independent of whether Gilbert was working. What does the results suggest about the guilt or innocence of Gilbert? All right, so we're going to think a little bit about that last part when we're all done with the analysis. But let's start with our null and alternative hypothesis. So this is example C. What should I write for the null hypothesis? HO. Johnny, you want to give that one a shot? Let me flip back to the problem here. What can you write there? Victoria?
Gilbert working or not working is independent from the number of deaths during a shift.
Okay, all right. So whether or not Gilbert was working is independent of deaths on a shift. Okay, so that's good. Has my needed buzzword here. It describes the row and column variables adequately. The alternative hypothesis is going to be there's an association between whether or not Gilbert was working and deaths on a shift. There is an association between whether or not Gilbert was working and deaths on a shift. Okay, let's go with that. Now, inasmuch as we're talking about somebody's freedom, talking about a murder case, appropriately they chose to do alpha as 0.01. So that brings us to our third step, which is inputting the data. Let's go back to the handout. So the data that we want to put in is 40, 34, 217, and 1350. Okay, let's put that in. Let's clear out all the old data and type in 40, 34, 217, and 1350. Okay. Analysis, contingency tables, columns 1 and 2, and let's change this to 0.01. It's not going to change your p-value if you forget to update the significance level. So you'll be okay there as long as you're doing this test based on the p-value. And wow, this is an incredibly high test statistic. Considering that your critical value, the point at which you would reject, is 6.6, we were well past that. Okay, so we've input our data. Our p-value is again a bunch of zeros. Elijah, what's that going to say about the null hypothesis?
We're going to reject it.
Yeah, p-value is low, H naught must go. H naught. Beautiful. So our conclusion then, based on this analysis, could be that the data support the alternative hypothesis, or that you can say the data reject the null hypothesis. I'm going to view it as supporting the alternative hypothesis. The data support the conclusion that there is an association between whether or not Gilbert worked and deaths on a shift. All right, as you copy that down, I want to ask you a follow-up question. I want you to think about it before anyone starts to answer. Can this analysis, can this data be used to help somebody be convicted in court? Think about it, and I'm going to ask you to talk to a neighbor. But I want you to think about it for yourself for a few seconds first. And now turn to a neighbor and argue it all out. What do you think? Online, you can throw in some stuff in the chat too.
Definitely not inside.
Just asking my personal opinion based on the data, I just definitely feel that.
Okay, well, let's move
Okay. Did you reach your conclusion? Can we convict her? Can we use this evidence in an actual jury trial?
Maybe.
Yeah,
only an association.
Use it. Solely decide.
not a deciding factor, but it's
So-
certainly a important piece of that.
So here's what happened. They use this in the grand jury. And the grand jury is basically saying, all right, is there enough evidence to take to an actual trial? And the answer there was yes. But in the actual trial, they did not use this data. All right, this data only shows that there's an association. It doesn't show causation. So what they did was they followed her and they caught her stealing supplies of epinephrine. And then they convicted her. So, yeah, you can't just say that, oh, gee, look at this data. I mean, could be confounding variables like our ice cream example just a minute ago. What if it was somebody else who happened to work on the same shift with Kristen Gilbert? All right, in that case, they're the real cause, not Gilbert, but Gilbert is getting convicted on this association, and that's all it is. It's an association. So, but this actually did happen.
I thought it was a guy.
Yeah.
Yeah, wasn't it?
It-
It was like,
This is the actual real case. I'm not familiar with the Netflix one.
oh, it was like based on a true story. It was
Well,
like,
Well, they could have changed the gender real easily.
well,
Now,
it was
Is it
like,
black?
it was a nurse.
It also.
No, Kristen
Like
Gilbert,
three-
that's the real, one second.
Yeah.
Yeah,
If you-
Kristen
Speech
Gilbert
different, so she.
is the real, that's a real lady, it's a woman.
yeah, it was
That's a woman, that's her name is Kristen Heather Gilbert.
she did it to impress her boyfriend because she wanted to be this heroic rescuing angel that swoops in at the nick of time to rescue these people who are suffering a heart attack. So that's what I remember about the case, but it was a woman. So
If you die, you die. Good luck.
yeah, it's like, all right, you better hope I get there in time. I don't know. It's pretty sad. Pretty sad. Okay, let's keep going.
I'll give it.
So my big point there was that chi-squared tests are used for association, not causation.
There's a lot of stuff.
All right,
That's
Let's-
someone from Twilight.
That's a very,
No, it's real, I saw that
It is real.
let's do one last one here. Actually, maybe kind of two at the same time. There's, folks, if I can get going, please. So here's some data, and let's just work on this little part here. And I'm sorry I don't have it written out in terms of a table, but this is whether or not men or women got accepted to University of California, Berkeley. Pretty sure that's where this data comes from, so this is example D.
Isn't this on Google Doc?
Yeah, it is in Google Docs. There is a link that I put online for you, so you can pick up the data that way. Yeah, it's on the announcements section. So let's see. Nope, not there. Not here. Yeah, course home. If you click the announcements, you should be taken to the data set. Not that it's all that hard to enter. There we go. So that's the little subsection of data we want. This is the number of women who are, men and women who are accepted and rejected at University of California, Berkeley. So initially this looked pretty bad. Accepted and rejected. Men and women. 632, 291, and 518, and 391. Okay. Is there an association between gender and acceptance as far as UCal Berkeley's admissions data is concerned? Well, let's run a hypothesis test. The null hypothesis would be, I don't know, somebody give me that null hypothesis. What do you think, Gabby? What's the null hypothesis gonna be?
They're independent.
Be a little, be specific enough for me to grade you on.
Acceptance rates between, acceptance rates for University of California, Berkeley, and the gender of the applicants are independent.
Okay. Acceptance rates. Rates at UCal Berkeley and gender are independent. Lush. And the alternative hypothesis is that there is an association between gender and acceptance rates. At University of California, Berkeley. Yeah, it wasn't at. God, that looks awful. Now, I haven't given you an alpha on this one. So let's decide on alpha for ourselves. What do you think we should use for alpha?
0.05.
0.05? Okay. Let's enter our data. So that's this next step here, and we're gonna enter data from this table. Stat disk. Let's clear out the old stuff and bang away at the new stuff. 632, 518, 291, and 391. Okay. Analysis, contingency tables, 1 and 2, 5%, so I think we're looking good. Clara, what am I looking for from this table, or from this output?
The p-value,
And what's the p-value?
0.
Good. P-value is essentially 0. So Gerald, what's the p-value telling us to do with regard to our null hypothesis?
You have to reject it because the what's it called? The alpha is bigger than the p-value because the p-value is 0.
Good. And what's our little mantra that helps us out here?
If it's low, if p-value is low, HO has to go.
Yes, good. If the p-value is low, HO has to go. So, good job. We're gonna reject H naught.
Are all these type of problems gonna be rejected?
No,
Okay.
no. I mean, I was thinking about that in my morning class. I'm like, we got rejected in all these. Kind of regard that.
Is it rare to fail to reject?
No, it's not necessarily rare. Yeah, but it's kind of an interesting question. How come we always see these things reject? There's literally what's called a file drawer problem when people publish results. Typically, if you publish results, you want to get something significant. You want to be able to reject. And a lot of times, if you have a result that's not significant, then you just put it away. You don't bother trying to publish. And it's literally called the file drawer problem because there's a lot of work that's done. Oh, we didn't get below alpha's 5%. People file it away. They just don't publish it. So you're not going to see that. Now, my guess, and we could try this if you'd like, the class is roughly split between males and females. We could decide if, amongst males and females, do you like Coke or do you like Pepsi? And my guess is that there'd be no association there. They'd be independent. So a lot of things like that are gonna be independent. So we can take the time to do one like that if you'd like. We'll finish this one up and then we'll decide on a bonus problem here. Let's see, so reject. There is sufficient evidence to support the claim that there is an association between gender and acceptance rates. So wow, this looks bad for you, Cal Berkeley. And when school administrators got a hold of this data, like, uh-oh, there's a problem. And wisely, they gave it to one of their mathematicians and said, here, look into this. And they literally did. Now, when I went investigating this problem and getting the actual real data on this, they didn't actually list the department names. So I don't know what departments they were talking about here. But here's what was going on. Men and women here were typically applying to different programs. So there's a lot more men that applied to, say, Department A, where they had a 62% acceptance rate. But take a look at how women did in this department. They had an 82% acceptance rate. Whatever Department A is, they're not very discriminating, right? They're not taking the 5% of the very best. They're just saying, okay, yeah, looking good. But Department C was a little bit more discriminating. A little bit more than 1 in 3 got accepted in Department C. But the reason that these results here look so bad is because there's a lot more women applying to Department C than Department A. So this is dragging down the results overall for women because a lot more women are applying to a tougher program and not getting in. So that's something called Simpson's paradox. But just be aware that these contingency tables might not always tell a complete story. You're just going to have to be careful. That's probably why they say that there's 3 kinds of lies, damn lies, and statistics. So anyways, comments or thoughts on this one? Yes?
Would legacy admissions be a factor in that? Because I know in Ivy Leagues, that's a large reason why certain groups are.
Sure, it could be. It could be. This analysis doesn't account for legacy admissions. I know that at least at the University of Michigan, they're not using legacy data anymore, at least for the parents. I did hear that, if your grandparent went to the University of Michigan, that might help out. But I don't know. I think that there's problems with that. And I would guess that they've done away with it, but I don't know.
Yeah, because since men were more likely to go to college in the past and it's becoming more common, you would think that there would kind of be a skew there.
Yeah, there could be a skew there. Yeah. So the idea of using legacy biases not only against women but against minorities too. So there is a problem with using legacies as part of your criteria for admitting that. Like I said, as far as I know, that practice has been at least diminished. So, other questions or thoughts on contingency tables? Looking good here? All right. Should we try our own data set? Nah, I'm not seeing a lot of enthusiasm for that. All right. Good enough.